Alright, so in this video we're going to continue this problem here, and we're on part C. Part C is asking us to find the region R, it's telling us that the region R is the base of a solid. So now we're assuming that this here is a base of some type of solid, and then for this solid, each cross section perpendicular to the x-axis is a square, and then we want us to find the volume of that solid. Well, what does that mean? Well, imagine if you were to lay this thing flat on the floor. Pretend this is flat on the floor. You're looking at this as a this is we're having a top view here. But imagine if you were to tilt this shape, you would have maybe something like this. So if you were to just tilt this figure a little bit, maybe you'd have something that looks like this. So you'd have some type of shape that looks like this. And think that this shape is rising, so you have some type of solid coming off. This is the base, right? This orange region here. This orange region here is the base. That's the base that they're talking about, which is the base that you see here. Now, all they're telling us is that from this base we have some type of solid, maybe something like this. Maybe it goes like in different heights, so maybe it goes up and then down. So but each solid, or each cross section perpendicular, I should draw it like this maybe, is a square. And think about just adding up infinitely many squares. Then you would get some type of solid region, and maybe some are a little higher, we don't know, and then some are a little shorter. But the whole point is that we're stacking a bunch of squares on top of this region. So how do we find the volume of this? Well, we go back to our method of finding volume, and that's just slicing things up and then adding infinitely many slices to get the volume. So that's what we're going to do. If I imagine taking a slice here, so let me just take a slice perpendicular to the x-axis as the problem states. So I can imagine that my slice is maybe this one right here, right? So that my slice is this guy right here. So there's my slice, there's my square. And I'm going to pull this out, but before I pull it out, I'm going to go ahead and give it a width of delta x. So again, if I imagine this slice that I made, this is a top view of the slice, but if I want to look at the whole thing, it's going to look something like this maybe. So maybe I'll have something like this. So there's my square. And here's my, again, this part that you see right here, that would be considered the top view that you see on this graph here. So we have something like this, and I labeled that this was a width of dx, which means that this is the same thing, so this is also dx right there. Now because this is a square, we know that this side right here is the same length as this side, right? Well, what is the length? So what is the length of a side? Well, it's going to be the distance from here to here, right? Well, what is the distance from here to here? Well, again, this is 6, and this is the height here. The height here is given by this curve, this function here, for ln of 3 minus x. So the distance here is actually just 6 minus the bottom function, right? It's kind of like the area between curves, right? So it's the top minus the bottom. So it'll be 6 minus 4 ln 3 minus x. So again, this distance from here to here is 6 minus 4 ln of 3 minus x. But again, remember, we're talking about a square, so that means that this distance is also 6 minus 4 ln 3 minus x, right? Again, because a square has the same sides, and we have a square here. I mean, that's what the problem is telling us, that this is a square. Well, my question to you is, how do you find the volume of this figure here, of this solid? Well, it's just length times width times the height, right? It's just the length times the width times the height. So we can think about the volume. We can think about the volume of one of these squares. I feel weird calling it a square because it's not a square. A square is a two-dimensional shape, and here we have some type of three-dimensional shape. So we can think about it like a square, or maybe like some type of square prism. I misspelled prism. Prism. There we go. Alright, so we can think about this as the volume of one square prism or something. Um, Not necessarily a cube, but some type of prism here. So what's the volume? Well, it's just the length times the width times the height. The length times the width times the height. And if we start plugging things in, I can think about this as the length if I want to. So I can think about this side right here as the length. So it'll be 6 minus 4 ln 3 minus x times the height. Well, maybe I can think about this guy as a height, right? Or you can think about this guy as a height and maybe this guy as a length. Maybe that might make a little bit more sense. Or times the width, I'm sorry. So this might be the width. Well, it's going to be times another 6 minus 4 ln of 3 minus x. And then what do we say the height was of this function? Well, the height was given by this width here that we called dx or delta x. So times our dx there. Well, I can kind of simplify this and maybe rewrite this as maybe 6 minus 4 ln of 3 minus x, right? 3 minus x squared, since I have two of them, dx. And if you think about this, this is the formula, the area of a square. The area of a square is equal to s squared, where it's just s is the side, so side squared. Well, that's kind of what we have here. 6 minus 4 ln of 3 minus x is a square, or I'm sorry, is a side to the square. And then we're squaring that since the length of each side is the same. Now this dx comes because now we're adding some depth to it, and we're adding some type of dimension to it, some type of 3D. We're making it three-dimensional, I should say. Now, how do you calculate the volume of the entire region? All we've done so far is calculate the volume. We're now able to calculate the volume of one single square prism. But how can we do the entire region? Well, again, imagine this idea of doing infinitely many squares, and if you do infinitely many squares and you add them all up and you make them extremely thin, then you would eventually get this whole figure. You'd get the whole volume of the entire figure here. So that's the goal. Well, if we're going to be accumulating infinitely many things, then we better be taking an integral. So that's exactly what we're going to do here. So, oops, let me see. Did I run out of space here? Well, let me go ahead and write it like this. So the volume is going to equal this thing right here. The only difference is that we now need to accumulate. We need to accumulate infinitely many squares, and we're going to be going from 0. Again, if we look at our picture, it looks like we're going from 0 to 2. So we're going to be going from 0 to 2. And because this is a calculator question, we don't need to do this by hand. I'm not sure if one would even be able to do this by hand, maybe using a table of integrals of some sort. But anyway, we're going to plug this into our calculator, and if you do the math, or you plug this in and allow your calculator to do the math for you, then we get an answer 26.66, or if you round up a little bit, I'm sorry, 26.666 or 26.667, however you want to look at it.